Here are the two diagrams showing a car is taking turn. In the first diagram, the car is moving on the horizontal circular road, and the second one, the car is moving on the banked circular road. In horizontal circular road, the angle between car and the road is 0, so theta equals to 0. And in banked road, there is an angle between horizontal surface of the road and the vehicle is theta. Theta is called angle of banking. This is horizontal surface of the road, and even the vehicle is horizontal to the surface. But here the vehicle is not horizontal to the surface. We made the road purposely inclined, making some angle theta with horizontal. Here we made the road, one side is more heighted, so this part is more heighted, so one side of the road is more heighted. Another part of the road is touching the ground, so we made the road like this. So this is actual road. So the one side of the road is more heighted and another side of the road is almost touching the ground, almost touching the horizontal surface. So this is the car. This is a car and these are the wheels touching the car. We can say vehicle. So this is the car or vehicle. It can be the any vehicle, not exactly be the car. It can be the even bicycle. So it is a vehicle, as well as this is the vehicle. So there is an angle theta between the horizontal surface of the road and inclined surface of the road, and that theta nothing but called as a angle of banking. First we'll understand vehicle taking turn along the horizontal circular road, and this is a circular road, so we assume that it is a complete circle like this. In fact, it is not a circle, it is a part of the circle, but we assume that it is a complete circle like this. And this is the R, the radius of the road, that is a R. So R is a radius of, and the road is horizontal, so R is nothing but radius of horizontal circular path of the road. And here I have drawn the vertical section of the car. This is the vertical section of the car. Let C be the center of the circular path, and for all calculation purpose we assume car to be a particle, and in place of the car we can use any other vehicle, like we can use bicycle, it is applicable for even truck, it is applicable for even any type of tempo, or it can be even applicable for a train. When the vehicle is taking the turn, there are the multiple forces acting on the car, and one of the force is nothing but centripetal force. This centripetal force is pulling the car toward the center. So the car is moving from this position to this position due to the centripetal force. So car will skid off, but there is a force of friction. This force of friction prevents the car from the skidding off and maintain its circular motion. The moment centripetal force more than the static friction, then the car will move toward the center of the circular path. This is nothing but called skidding of the car. The weight of car, that is W equals to mg, is acting in the downward direction, and the normal reaction is acting in the upward direction. Suppose C is the center of this circular path and R is the radius. R is the radius of horizontal circular path. Let Fs be the force of static friction. And the centripetal force mr omega square, it is also equals to mv square upon r. So centripetal force mr omega square or mv square upon r. So what is omega? Omega is the angular velocity. Angular velocity of the vehicle. We can have another one, v is the linear velocity of the vehicle. When the vehicle is taking the turn, the important condition is that the centripetal force, that is a mr omega square, must be less than the force of static friction. That means as the vehicle taking the turn without skidding up, the important condition is that the centripetal force must be balanced by static friction, force of static friction. Then only the vehicle will not skid off. So this is the condition for vehicle not to skid off. For not skid off. So when vehicle is not skidding off, the condition is mr omega square equals to force of static friction. And moreover, the normal reaction has to be balanced by the weight of the car. This is general. It happens with every object. Whenever the object is resting on the ground, normal reaction is always equals to the weight of the body. So we have the two conditions. One condition is N, normal reaction must be equal to weight of the body, and the force of static friction must be balanced by the centripetal force. So these are the two important conditions so that the vehicle will move easily without skidding off along the horizontal curved surface. It is a horizontal circular path. So we have the two equations. One is the N equals to mg, another is the Fs equals to mr omega square. Call it as a 1 and 2. Now dividing 2 by 1. So we get here Fs upon N equals to mr omega square divided by mg, and this get cancelled. So implies Fs upon N equals to r omega square divided by g. Now suppose we have this vehicle for some speed v1, the force of friction is Fs1. For certain v2, there is a force of static friction Fs2, and v2 is greater than v1. Now v3 is, for the v3, the speed of v3, the force of static friction is Fs3, and v3 greater than v2. Like this, if we keep on increasing the speed of the vehicle, the force of static friction will also increase, and the force of static friction will acquire certain maximum value. We can call it as a F max. So we cannot increase the speed of the vehicle beyond a particular limit. If you increase, what will happen? If you increase the speed of the vehicle beyond a limit, then what will happen? The centripetal force will be greater than force of static friction and the vehicle will skid off. Therefore, you should not increase the speed of the vehicle beyond a limit for the safely driving along the horizontal curved path. So there is a limit to increase the speed, because there is a limit for value of the magnitude of the static friction. And one more thing, that we know that V equals to R omega. So omega equals to V upon R. What is omega? Omega is angular velocity and V is the linear velocity. So this is linear velocity, and omega is nothing but angular velocity. So this is the relationship between linear velocity and angular velocity. So here is omega, r omega square upon g. So in place of omega, we can put here omega equals to v upon r. So what I am having, fs upon n equals to r omega square upon g, and this is equivalent to r in place of omega v upon r divided by g. So here r into v square upon r square multiplied by g equals to v square upon rg. So ultimately what we have here, fs upon n equals to r omega square upon g equals to v square upon rg. This is the condition for what? Horizontal curved rod. Here I already told you that as v increases, static friction also increases, and static friction acquires certain maximum value. So for V max there is maximum value of static friction, can be denoted by Fs max. Therefore, above equation can be written as Fs max upon n equals to v square upon rg. And we know that static friction upon normal reaction equals to mu s. For Fs is the static friction, n is the normal reaction. So Fs upon n equals to mu s. So implies this is a mu s equals to v square upon rg. But v is the maximum value. Therefore what I can write here, suffix v max square. Here also v max square. Implies v square max equals to mu s rg. Now taking square root both sides, so we get v max equals to under root of mu s rg. So this is the maximum linear velocity of the body taking turn along the horizontal curved road. This is the maximum possible speed of the vehicle. And why we are using the word speed, not velocity? The reason is that here we are not taken into account the direction. We are just talking about the magnitude of the velocity. So magnitude of velocity nothing but called as a speed. Therefore it is a maximum speed. It can also be denoted like Vs. So Vs equals to under root of mu s rg. And what is the mu s? Mu s is nothing but coefficient of static friction. Coefficient of static friction between tires and road. After this, let us talk about how to get the expression for velocity in case of the banked curved road. It is a banked road, actually I need not speak curved. So banked road or already curved road. So let us develop now expression for maximum speed for the banked road. In case of banked road, one side is more heighted, another side of the road is touching the ground. So this is the raised height. And other part of the road is touching the ground. So the road is making some angle, the surface of the road, the final surface of the road making some angle theta with the horizontal surface of original road. You see, banked road are already not there. We have to make them. We have to construct them. So with the horizontal, it is making some angle theta. So theta is the angle with horizontal. And the weight of the vehicle is acting perpendicular to the ground. So, and it is acting in the downward direction. And the normal reaction is perpendicular to surface of the road, that is perpendicular to AB. The normal reaction is perpendicular to surface of the road, that is the AB. AB is the final surface of the road. AB is the final surface of the banked road. And the normal reaction, this is a normal reaction, and it is perpendicular to AB. Now we can get the two components of normal reaction. One is the vertical component, another is the horizontal component. This is the horizontal component and it is a vertical component of normal reaction, and this angle is theta. So this is vertical component and it is horizontal component. This is vertical component of normal reaction. And it is horizontal component of normal reaction. Now joining this one and this one, so we completed the parallelogram. Now we need to find what is horizontal and vertical component. So here in this derivation, I am neglecting the coefficient of static friction. There are the two situations to find the angle of banking: with static friction, with consideration of static friction, and without consideration of static friction. So here in this video, I am developing angle of banking without the static friction. I am neglecting the amount of the magnitude of static friction. Now here I have completed the triangle now. So I need to find out the horizontal and vertical component of normal reaction. From the diagram, I have sin theta. Sin theta equals to PQ upon OP. OP nothing but normal reaction. Therefore, I got horizontal component PQ equals to OP sin theta. OP nothing but N. Therefore, PQ equals to N sin theta. PQ nothing but horizontal component of normal reaction. Now we'll find out vertical component. For that, I need to consider cos theta. Cos theta equals to OQ upon OP. Therefore, OQ equals to OP cos theta. What is OP? OP nothing but normal reaction. Therefore, we got OQ equals to N cos theta. So we got here horizontal and vertical component of normal reaction. OQ is a vertical component and vertical component of normal reaction, and it is exactly opposite to the weight of the body, weight of the car. So OQ is in the upward direction and OQ nothing but N cos theta. So this is the vertical component N cos theta, and OR is the horizontal component, and OR nothing but given by PQ, and PQ nothing but N sin theta. Therefore the horizontal component is PQ, that is OR, that is equals to N sin theta. Here the vertical component N cos theta is balanced by the weight of the body, so N cos theta equals to mg, and the horizontal component N sin theta exactly balanced by the centripetal force, that is mv square upon r. Call it as equation 1 and call it as equation 2. I already told you that here in this expression, in this derivation, I have neglected the presence of static friction. Now dividing equation 2 by 1, so N sin theta upon N cos theta equals to mv square upon r divided by mg. This is nothing but mv square upon r into 1 upon mg. M get cancelled and left side n get cancelled, Sin theta upon cos theta nothing but tan theta. In RHS we have V square upon RG. So we got here the expression for angle of banking, that is tan theta equals to V square upon RG implies theta equals to tan inverse of V square upon RG. This expression developed without considering static friction. We had assumed the presence of static friction is almost negligible. So after considering no static friction, we got expression for angle of banking equals to tan inverse of V square upon RG. One more thing, from this expression we can find out the speed, the most safe speed of the vehicle, that is V square equals to tan theta multiplied by RG. Therefore we get here V equals to under root of RG tan theta. This is the most safe speed, maximum most space speed for the vehicle on the road, that is V equals to under root of RG tan theta. So here in this video I had considered only presence of normal reaction. In next video I shall be considering presence of the even static friction. So I shall be getting normal component and vertical component of static friction. I hope you got the idea how to develop the safe speed of vehicle on a banked road. Meet you again with another video. Till then, wish you good luck. All the best.